happy return. So Hooke's Law. So when you're studying forces, you may run into this when you're going to be talking about springs. So now in Hooke's Law, what happens is that if you attach, for example, any kind of a mass, it doesn't have to necessarily be a mass. If you just have a spring on its own and you start to compress it, now you know that if you compress a spring, you will have a sense that the spring wants to push back. It wants to return to its normal, length, as it goes through. If you expand it, so if you kind of take the spring and start to extend it a bit. So as you're extending it, again, you will notice that the spring will pull back and it will want to once again return to its normal kind of position as it's set, so kind of its normal size. So any compressions that you have or any extensions of a spring that you will have, it will always try to return you back to normal. Now, this isn't something that you need to necessarily test out. You can kind of sense it, especially if you've worked with springs at all. Now, so here's an example where you do have some kind of a mass. And now I have labeled, as you can see there on the x-axis, there is a certain amount that you can actually compress, right? So you can compress this a certain amount this way, you can expand it in this particular way, and obviously the spring is going to look a little bit different. So for example, boom, voila. So here is the compression that you have, and then here's the extension that you have. So what I am referring to is that in this particular case, you will notice that there's going to be a force which is going to want to try to push you back in this direction. And in the second case, there's going to be a force which is going to want to try to kind of pull you back in this direction. So we call this the force that the spring is going to be exerting on you, that you will have. Now, by the way, these springs, they don't have to be horizontal. They can be vertical, right? So I can change this whole thing and I can, again, make a reference with respect to the y direction. And instead of talking about an x, you can certainly talk about an y. And I'll refer to that in just a moment. But when you are doing this, what Hooke has found is that for springs, you have this very nice relationship, which you have. So you have this k right here. Now this k is a constant, and it's sometimes called as Hooke's constant for springs. And you have this delta x. Now you should be familiar with delta x, which is just nothing else but your final position minus your initial position that you will have, within here. Now we'll assume that the initial position is kind of the starting position within here, and most of the time we assume that this is stuck at 0. And that's a good position to have, and therefore very often even this delta might just be dropped, and you have Hooke's Law just simply written out as simply in this way. You may not necessarily have an S for the spring in there, because sometimes it might refer to static friction if you talked about that, but in this case we're talking about springs. So you have a very simple, it's a linear relationship that you have. Now this negative, right, all that it means, and if you're talking about vectors, so this is still a vector in here. Now the negative just means the direction that you would have. And so as you're going through, if you would be actually working this entire thing, it just tells you that it is on the opposite side. So you kind of should know what the direction will be when you're compressing and then when you're expanding the actual spring. So that direction, this very often sometimes will also be dropped, and you just simply have this as kx, which then definitely looks very much like a linear relationship. Now this only actually acts for a certain range that you would be doing for a spring. So, typically there will be some kind of a range between, within here, is that if you're going to be compressing or expanding the actual spring, that this relationship will hold, where it actually tells you what the force will be. Now you might wonder, what is this K? Like, where does it come from? Does every single spring have the same exact constant K? No, it doesn't, right? So this will actually be dependent on the spring that you have. So this K is typically found through experimentation for a certain spring. So different springs will have different constant K. And this just simply means, how far are you going to be moving, compressing, or expanding it with respect to, okay, the original position that you have in here. So as you're going through in here, so this would be your delta x, okay, and then in this case, this would have been your delta x if you're expanding it out. And again, so the way that I think about it, I don't really worry about the negative much. Sometimes I will just drop it entirely. And I will know that the negative is just simply relating it back to the direction, right? So it's all dependent on how you're going to be defining these x's, So if it's positive and as you're moving to the right, okay, so if you have a positive value, so let's imagine that we would have, okay, I'll just take an arbitrary number. So let's say that, we were able to move this spring, let's say maybe 0.5 meters in this direction. And this would have been your final position. So if this was your initial position right here, which was 0, and then you would do your delta x like right there, then what you would have is, well, your final position 0.5 minus 0, which is 0.5 in terms of its value. The constant k within here is always going to be positive, so it's a positive value that we have, this Hooke's constant, okay, for a particular spring. So if that's positive, so let's say that for this particular spring, I'm making this up, but let's say k was maybe 2, okay, that we would have in here. And therefore, if you were doing your calculations, your Fs would have been equal to, I'll drop the negative for the moment, but it would have been 2 for the k multiplied by, let's say, 0.5, and you will notice that this is just equal to 1. But 1 is just the magnitude, right? So as you can see here, this would have been in the negative direction with respect to positive. So hence we put this negative in here, right? So what you would have is it would have been negative 1 Newton within as you're moving along. And that negative just means it's to the left, right? So you can drop it and you can just say that the force is to the left. And the same thing happens. So if you did it, okay, in the opposite direction, then notice that this value right here, so maybe this was negative 0.5 with respect to 0 over here. So if you did xf, right, minus the xi, so your initial, you would have gotten, so within here, so this would have given you a delta x of equal to, and this would have been an actual negative value, so 0.5 because you moved to the left. So if you're substituting this back into the equation, Fs is equal to, and of course if you had this negative, let's kind of keep the same constant as 2 multiplied by negative 0.5, notice that it's going to be a positive 1 Newton. And of course the positive that we would have just simply means that this is to the right. So that's all that this means, okay, within the Hooke's law that you have in here. This k again is just based on whichever spring, so typically this might be given, or you can solve for it, right? I mean, we can easily solve if we had the actual x, okay, within here, and this was given to us experimentally, we can find out what that constant will be. So, typically, you would have that the constant k would be equal to whatever force the spring would exert over the actual distance that you have. And sure, you can put the negative in there if you like, okay, just to make sure that it's going to be, okay, with the correct constant k within here. But please keep in mind that the constant k is positive. So there you have it. So that's kind of how Hooke's law works, okay? And this is in the x direction because typically that's how it might be defined. But there is nothing to say that you can't take this right here. I'm going to kind of duplicate it within. I'm going to bring it back down. Nobody says that, you can't do this vertically, right? So you can still have a spring. It will have a certain, certain length. And then, of course, gravity might be acting on this as well. But the same style that you would have in here. Okay, so now the only thing is you need to draw your free body diagrams. In this case, you would have to kind of take into account gravity as well. So this will just depend on how that spring works. Now, most of the time when you're just beginning this and you're referring to Hooke's law, that's why they just will most of the time just write x because it is in the x direction, so which is horizontal in here. All right, so keep that in mind as you are studying this concept overall. So that is pretty much it. Okay, so with respect to Hooke's law, so when you are studying it, so the equation is rather simple. It is linear around a certain region. Doesn't mean that it's always going to be linear. The negative, just keep in mind that it's direction, so you can drop it if you will understand what happens when you compress a spring. Obviously, it's going to push back, okay, and if you extend it, it's going to try to pull itself back. So therefore, you know the directions, and then you can just worry about magnitudes. Okay? And the K can be given, or you can find it. And then finding the delta X, should be very understandable for you, especially if you've done any kinematics or positions and displacement and so on. So just remember that delta just means change between your final and your initial. And typically for springs, we assume initial is 0. So the delta really is the X value where you are located, okay, with respect to some reference point. All right, thanks for watching. I hope that you found this useful. Happy studying. Bye, everybody.